And good morning, students. So this class we are going to solve the problem, find the poles and zeros location of h of z. H of z is a transfer function. So what does mean by transfer function means, so the ratio of the output divided by input, and h of z which is equal to 1 plus 0.1 z power minus 1 divided by 1 minus 2.5 z power minus 1 plus z power minus 2. So then determine the inverse z transform of h of z. We first multiply z power z square to both denominator and numerator polynomials to obtain h of z which is equal to z into z power plus 1 divided by z square minus 2.5 z power minus 1 plus 1. So apparently they are two zeros, z is 0 and z which is equal to minus 0.01. On of the other hand, by solving that quadratic equation at the denominator polynomial, so the poles are determined as z which is equal to 0.8 and z which is equal to 0.125. And accordingly we have x of z, h of z which is equal to a1 divided by 1 minus 0.8 into z power minus 1 plus a2 divided by 1 minus 1.25 z power minus 1. Employing a is calculated as a1 into 1 minus 0.8 into z power minus 1 and h of z, where z which is equal to 0.8 and which is equal to minus 1 plus 0.1 into z power minus 1 divided by 1 minus 1.2 into 5 into z power minus 1, where z which is equal to 0.8 where which is equal to 2. So to find out a and b value, similarly a1 is 2 and similarly a2 is found to be minus 3. As a result, the partial fraction expansion h of z is h of z which is equal to 2 divided by 1 minus 0.8 into z power minus 1 minus 3 divided by 1 minus 1.25 into z power minus 1. As the ROC is not specified, we investigate all the possible scenarios, namely modulus of z greater than 1.25 and modulus of z greater than 0.8 and less than 1.25 and modulus of z less than 0.8. So for modulus of z greater than 1.25, we notice that 0.8 power n into u of n lies between 1 divided by 1 minus 0.8 into z power minus 1. So where modulus of z greater than 0.8. So and 0.125 n into u of n lies tends to 1 divided by 1 minus 1.25 into z power minus 1, where modulus of z greater than 1.25. That both ROCs agrees with modulus of z greater than 1.25. So combining the result, the inverse z transform h of n is h of n which is equal to 2 into 0.8 power n minus 3 into 1.25 the whole power n into u of n, which is a right side sequence and aligns with P5. So for modulus of z greater than 0.8 less than 1.25, and we make use of 0.5 the whole power a when 0.8 the whole power n into u of n lies between 1 divided by 1 minus 0.8 into z power minus 1 and modulus of z greater than 0.8. And next case, minus 1.25 power n into u of minus n minus 1 gives 1 divided by 1 minus 1.25 z power minus 1, where modulus of z less than 1.25. So where both ROCs agree with modulus of z less than 0.8 and less than 1.25. So this implies h of n which is equal to 2 into 0.8 the whole power n into u of n plus 3 into 1.25 the whole power n into u of minus n minus 1, which is a two-side sequence and aligns with P7. Finally, for modulus of z less than 0.8 means minus 0.8 power n into u of minus n minus 1 tends to 1 divided by 1 minus 0.8 into z power minus 1, where modulus of z less than 0.8 and 1.25 the whole power n into u of minus n minus 1 lies 1 divided by 1 minus 0.25 into z power minus 1, where modulus of z less than 1.25, where both ROCs agree with modulus of z less than 0.8. As a result, we have h of n which is equal to minus 2 into 0.2 the whole power n plus 3 into 1.25 power n into u of minus n minus 1, which is a left side sequence and aligns with the P6. Suppose h of n is the impulse response of the discrete time LTI systems So recall h of n which is equal to 0 where n less than 0. That is summation n which is equal to minus infinity to plus infinity modulus of h of n less than infinity. So the three possible impulse responses h of n 2 into 0.8 the whole power n minus 1 minus 0.25 power n into u of n is the impulse response of a causal and unstable system, and h of n which is equal to 2 into 0.5 power n into u of n plus 1.25 power the whole power n into u of minus n minus 1 corresponds to the non-causal but stable system, and h of n which is equal to minus 2 into 0.8 power n plus 1.25 power n into u of minus n minus 1 is non-causal and unstable. And case 2, m greater than or equal to n and all poles are of first order. In this case, x of z can be expressed as x of z which is equal to summation l which is equal to 0 m minus n bi into z power minus 1 plus summation k which is equal to 1 to n ak divided by 1 minus ck into z power minus 1. So here bi are obtained by long division of the numerator by the denominator with the division process terminating when the remainder is lower degree than the denominator. So can be obtained using example. So to determine the x of n which has a transform of the following: x of z which is equal to 4 minus 2 into z power minus 1 plus z power minus 2 divided by 1 minus 1.5 into z power minus 1 plus 0.5 into z power minus 2. So where modulus of z greater than 1, the poles are easily determined as z which is equal to 0.5 and z which is equal to 1. So according to the m which is equal to n which is equal to 2 by x of z which is equal to b naught plus a1 divided by 1 minus 0.5 into z power minus 1 plus a2 divided by 1 minus z power minus 1. So the value of b naught is found by dividing the numerator polynomial by the denominator polynomial as follows: 0.5 z power minus 1 minus 1.5 into z power minus 1 plus 2 into 2 z power minus 2 to minus 2 into z power minus 1 plus 4, and z minus 2 minus 3 into z power minus 1 plus 2 divided by z minus 1 plus 2, and that is b naught which is equal to 2. So thus x of x is expressed as x of z which is equal to 2 plus that term 2 plus z inverse divided by 1 minus 0.5 into z power minus 1 into 1 minus z power minus 1 which is equal to 2 plus a divided by 1 plus 0.5 into z power minus 1 plus a 2 into 1 minus z power minus 1. So according to a1 and a2 are calculated as, and a1 which is equal to 4 minus 2 into z power minus 1 plus z power minus 2 divided by 1 minus z power minus 1 which is equal to minus 4, and a2 will be 4 minus 2 into z power minus 1 plus z power minus 2 1 minus 0.5 into z power minus 1 where z which is equal to 1 which is equal to 6 where modulus of z greater than 1, and 0.5 power n u of n where 1 divided by 0.5 into z power minus 1 modulus of z greater than 0.5, and u of n lies between 1 divided by 1 minus z power minus 1 modulus of z greater than 1. So the inverse z transform of x of n is linear, and x of n which is equal to 2 into del of n minus 4 into 0.5 power n into u of n plus 6 into u of n. In case 3, m less than n with multiple order poles. If x of z has a order pole at z which is equal to c with s greater than 2, this means that there are x repeated poles with the same value of c1. X of z is x of z summation k which is equal to 1 and k not equal to I which is equal to n, ak which is equal to 1 minus k ck into z power minus 1 plus summation m which is equal to 1 to s cm divided by 1 minus c1 into z power minus 1 the whole power m. So when there are two or more multiple order poles, so we include a component like the second order term for each corresponding pole, and a1 can be computed according to 5.53 equation and calculated from cm which is equal to 1 divided by sm minus m in minus c1 into s minus m into d into s minus m divided by du s minus m 1 minus Cs of omega s into x of omega minus 1, where omega which is equal to C1 minus 1.